and let me start recording. Wait, what? What is this? I don't know what it's doing.
It looks like it's going.
I think it's going. Okay, cool. So now we're back to math. So let me just recall what we did last time. So we started looking at Coxeter groups and Coxeter systems. So we said here WS is a Coxeter system. And so here this means that S is some set. It's called the set of simple generators, or I might call them simple reflections. And these will be the generators of our group. W is the Coxeter group. And there's a presentation where we can write W as the group generated by S with the condition that, so we have these relations that S times S prime. Okay, this is gonna annoy me. I'm gonna break a lot of chalk. So S times S prime to the power of some number M of S comma S prime is the identity. And here, these numbers M of S comma S prime satisfy, first of all, that M of S comma S is always 1, and this is just saying that S itself is an involution, so each one of these simple generators, if you square it, you get the identity. And then also M of S comma S prime is always equal to M of S prime comma S, and this will be some positive integer. Well, okay, let me say it's at least 2, or it's infinity, if S and S prime are distinct. Okay. So these are Coxeter groups. And actually, let me clarify one thing that I said last time with this proposition here. So this is proposition 1.1.1 in the textbook by Bjorner and Brenti. And so last time I was asked this question, which was, here we have this presentation, but could it be possible that the order of S times S prime is actually smaller than M of S comma S prime? Like what this is telling you is that the order of this element S times S prime, it divides this number M of S comma S prime, but could it maybe be smaller? And the answer that I gave was no, but it's possible that maybe the way I answered this made it seem like this was obvious, and it's not obvious. So this is something that's proven in chapter 4 of the book, so I'm not going to prove it right now. But it's just good to know this, that the order, well, okay, let me say for S and S prime simple generators, the order of this element S times S prime is actually equal to M of S comma S prime. So this is saying that if you take this element to the power of M of S comma S prime, you get the identity, but there is no smaller power that you could raise it to get the identity. Okay? Catherine?
I have a stick of Hagroma. Do you want it?
You what?
I have a stick of
Oh, yeah, that would be awesome. Thank you. Okay, let's see if this works better. Okay, so at the end of class last time, I was sort of listing different Coxeter groups, and I was representing them with their Coxeter graphs. So remember, the Coxeter graph is a way of representing this data where you have a graph where the vertices are the simple reflections, and you connect two of them with an edge when they don't commute with each other. And if the M of S comma S prime is at least 4, then you put that number as a label for the edge. So let me give a couple other examples of this. So we could take this Coxeter group that looks like this. Okay, so last time I drew this example where this would be the symmetric group. But here I'm going to change it just slightly by labeling this edge with a 4. So this is saying that I would have, let's say this is S0, S1, S2, S3, and it goes all the way over to S sub n minus 1. Then this is just saying that it's the same kind of relations that the symmetric group satisfies, except now you have this S0 and S1, their product has order 4. And this is called the hyperoctahedral group. So this is the nth hyperoctahedral group. And it's often denoted by Bn. And there's a concrete way of thinking about it in a sort of combinatorial way. So just like you have the symmetric group, which you can think of as permutations of the numbers from 1 to n, this can also be thought of as what are called signed permutations. So this is the group of permutations of the set negative n through negative 1, and then 1 through n. Well, okay, I'll finish this sentence in a second, but first of all, this is just the set of integers from 1 to n and their negatives. And this should have, so it should be the group of permutations of this set with the following property. So such that, so let me call this group of permutations W of this set, such that W of negative I is negative W of I for all I. So you can check for yourself that this is a group, in the sense that if you multiply two permutations with this property, then the product actually still satisfies this property. And also, I'll just note, so Bn is isomorphic to a subgroup of S sub 2n. So the symmetric group on 2n numbers. And that's just because the symmetric group S sub 2n is going to be the group of all permutations of 2n numbers. Normally I would think of it as the numbers from 1 to 2n, but you could also just rename the numbers and say it's the group of permutations of these elements. And then if you add in this additional condition, then you get a subgroup of S of 2n. Okay? Let me also mention that there's so in the case of the symmetric group, remember there's a one-line notation that you can use to represent a permutation. And similarly here, there's a one-line notation. So the way we do this is, okay, let me phrase it this way. Elements of Bn are called signed permutations. And they have a one-line notation which looks something like, let's take, say 2, 1, or 3, but I'm going to put a bar over some of the numbers. And what this means is it's saying that 1 gets mapped to -2. The negative is because of the bar. I could write negative signs, but that gets a little confusing with the one-line notation, so it's easier to just put bars over them. So think of this as being -2, 1, 4, -3. So this is saying 1 maps to -2, 2 maps to 1, 3 maps to 4, and 4 maps to -3. And this uniquely determines the signed permutation because of this condition. So if I want to know, okay, well, where does it send -1? Then I say, well, W of -1 should be negative W of 1. So it should be negative of -2, so this should just be 2. And similarly, W of -2 should be -1. W of -3 should be 4, or sorry, negative 4. And W of negative 4 should be positive 3. And so in particular, let me just, oh, actually I should say what the simple generators are in this notation. So for 1 less than or equal to I less than or equal to n minus 1, Si will be the sign permutation that swaps the numbers I and I plus 1, but also simultaneously swaps negative I with negative I plus 1. So it's kind of like the simple transposition in the case of the symmetric group because it's swapping I and I plus 1, but you want to make sure that you're preserving this property, so you have to simultaneously swap negative I and negative I plus 1. So this is what these S1, S2, all the way to Sn minus 1 are. And then S0 is a little different. So S0 is just going to swap negative 1 with 1. And maybe one last thing I'll mention about the hyperoctahedral group is that the size, actually maybe I can ask, what is the size of this group? Like how many elements? Yes, so 2 to the n times n factorial. Because there are n factorial ways to write down this permutation, and then for each one of them I could put a bar over it or not, so I get 2 to the n ways to add the bars. Okay, so I wanted to spend a lot of time on this because this is like one of the most important Coxeter groups that people consider, mainly because a lot of times people will do things for the symmetric group, and there's some like maybe interesting combinatorial story that happens in the case of the symmetric group, and they'll say, oh, well, what would happen if we went to the hyperoctahedral group? And oftentimes they'll say, like, what happens in type B? So actually there's this sort of joke that when you go to an algebraic combinatorics conference, there are like 2 canonical questions that people will ask, like if you give your talk and then someone might ask a question. One of the canonical questions is there a Q analog, which is like sort of some refinement of the thing that you're discussing? And then the other canonical question is what happens in type B? And so this would be like someone presents something about symmetric groups or some kind of combinatorial objects, and then the natural thing is like, oh, well, what happens if you replace the symmetric group by the hyperoctahedral group? Maybe something interesting happens there. Okay. So, yeah, this is the hyperoctahedral group. Let me see what I have next. So actually, the next thing that I was going to discuss in my notes was Dn, but I think I won't because I added that on the problem set. So the problem set will be about a different finite Coxeter group called Dn. Okay, but now let me give another example. This will be an infinite Coxeter group. So far we've looked at the symmetric group. We've looked at, I guess, the dihedral group I mentioned briefly last time. This is the hyperoctahedral group. These are all finite groups, but there are also many infinite Coxeter groups. So this is the affine symmetric group. And, okay, so this is denoted by Sn tilde. This is the group of permutations of the set of integers, but satisfying a couple of conditions. So such that, oh, and I keep forgetting to write W. It's the group of permutations W of the set of integers, such that, first of all, W of I plus n is equal to W of I plus n for all I. secondly, maybe I'll make this a semicolon. Secondly, if you take the sum w of 1 plus w of 2 plus dot 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 plus w of n, this should be n plus 1 choose 2. And the reason that I want this to sum up to n plus 1 choose 2 is because the identity element of this group should be just the permutation that fixes everything, so just w of I equals I. And that will satisfy this condition, because 1 plus 2 plus dot 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 plus n is just n plus 1 choose 2. And the point is you want to preserve this sum throughout the group. Okay?
What is that non-trivial example of such a permutation?
Yeah, okay. Let me give an example. So let me write an example this way. Actually, let me do this. Yeah, okay, I'll give, yeah. So let's say I write, say n equals 4. And, here, okay, example, n equals 4. And I'll just write it by doing, okay, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and so on. So first let me write down the identity permutation, which would be, I'll just write, this is like the 2-line notation where I say -4 goes to -4, then -3, -2, -1, 0, 1, 2, 3, 4, 5, and so on. Okay, so this is dot, dot, dot. But now what I'm going to do is I'm going to swap 0 and 1, and I'll also swap, so I'll swap every number of the form 4k with 4k plus 1. So I'm going to swap the 0 and the 1. And I'll swap the 4 with the 5. And I'll swap the -4 with the -3. And I would continue this periodically. And you can check that we still have this condition. And also, if I add up the first 4 numbers, so I get 0 plus 2 plus 3 plus 5 is 10, which is 5 choose 2. And so the point is that, like when I did this swap, I decreased this number in this position by 1, and I increased this number in this position by 1, so the sum stayed the same. And actually, let me give this a name. So this will be little s0. So this is actually going to, this permutation I wrote down here is going to be one of our simple generators. And more generally, let's say, so let Si be, this will be the element that swaps each number that is congruent to I mod n with the number that's one more than it. So it's going to swap, well, I and I plus 1, or let me write it this way. It's going to swap I and I plus 1, but it's also going to swap I plus n and I plus n plus 1. And it's also going to swap I plus 2n with I plus 2n plus 1, and so on. And also going backward this way, it's going to swap, I guess, I minus n, I minus n with I minus n plus 1, and so on. Okay. I don't need the dots there. Okay. Now I guess, okay, the way I've written this, you could have done this for any I, but if I write down S sub 0 like this, that's the same as S sub n. So actually I only have n distinct elements here. And you can ask, what is the Coxeter graph? So I'm not supposed to write there, I think. The Coxeter graph is a cycle of size n. And there are no labels on any of the edges. So in this case, with n equals 4, the Coxeter graph would be S0, S1, S2, S3, and it's arranged like that. And one way you can kind of think of this is like, well, the reason that S1 and S2 have an edge between them which is unlabeled, right? This is saying that m of S1 comma S2 is 3, which is just like what S1 and S2 do in the symmetric group. And so it's kind of like S1 and S2 and S3, like this part here is sort of playing the role of the symmetric group, but you have this extra simple reflection that also has the same relation with S1 and S3. So it's like this kind of cyclic analog of the symmetric group in some sense. Maybe I didn't say that so well, but if you think about it, you can convince yourself that Si and Si plus 1 will have the same kind of relation between them as in the case of the symmetric group. Any questions about this? Oh, and let me just remark that this is an infinite group. Okay. The next thing I'll mention is that if you like polytopes, like the regular polytopes, their symmetry groups will always be Coxeter groups. So the symmetry group of a regular polytope is a Coxeter group. And these have been characterized, so I'll just write down the list actually. So here, I'll say you have some polytope in some dimension. Regular polytope. And then I'll draw the Coxeter graph of the symmetry group of that regular polytope. So in any dimension D, if I just take, D-dimensional Euclidean space, I can draw some polytope in it. So you can take the D-dimensional simplex. So the simplex would be, imagine you have these, simplex in 2 dimensions would be a triangle, like an equilateral triangle. And then in 3 dimensions, this would be like a tetrahedron, like a regular tetrahedron. And then you have analogs of these in higher dimensions. So in D dimensions, you'll have D plus 1 points. And they're sort of some analog of like a triangle. And the Coxeter graph here, well, this symmetry group here is just the symmetric group. So this is really SD plus 1. Right, so if you imagine like a triangle, then the symmetries are just given by permuting the 3 vertices in whatever way you want. And so you get permutations of 3 elements. But for a tetrahedron, you can permute 4 vertices in whatever way you want. So you get symmetric group S4, and so on for higher dimensions. Okay, then also in dimension D, there's a cube, or I guess maybe this would be called a hypercube for higher dimensions. So this would be like if you take the 0, 1 vectors, right? So any vector of size or of length d that has 0s and 1s, and those are the vertices of this cube. And here, the symmetry group is this hyperoctahedral group that I mentioned before. So you get BD, and as I said before, the Coxeter graph looks like that. So also, there's another d-dimensional regular polytope, which is the hyperoctahedron. And again, its symmetry group is the hyperoctahedral group, which is why this is called the hyperoctahedral group. So it's the same thing as this. And again, it's BD. Okay, and then there are some sporadic examples of regular polytopes that show up in other, there's one infinite family in 2 dimensions, which is easy. And this is just the M-gon. Right, so you can take a regular M-gon. And maybe this is kind of bad. Let me just do this again. The symmetry group of a regular M-gon is the dihedral group of order 2m, and this is the Coxeter graph, I2 of m. So I think in the homework I said to justify this, you can't just cite me and say like I said it in class, but yeah, this is the the dihedral group, and it's denoted by I2 of m. Maybe I'll say a little bit more about why these weird names are showing up in a little bit, but for now you can just say, okay, for some reason the dihedral group is being called I2 of m instead of dm or whatever. Okay, and then in 3 dimensions there are 2 regular polytopes called the dodecahedron and the icosahedron. So we have the dodecahedron and the icosahedron. And their symmetry groups are the same. And this is what's called H3. And the Coxeter graph just looks like this. You have 3 simple reflections, and this edge is labeled by a 5. It's the same thing here. And then in 4 dimensions, there are 3 other regular polytopes, and they have less creative names. So they are called the 24 cell and the 120 cell and the 600 cell. And the symmetry group of the 24 cell is called F4. So that looks like this. And then for the 120 cell and the 600 cell, they have the same symmetry group, which is called H4. And it's 4 simple reflections with these edges, and this edge is labeled by a 5. And these are all of the regular polytopes in various dimensions. Okay, so anyway, I guess the point of this is if you care about like regular polytopes and polytopal geometry, then Coxeter groups show up there. So let me also mention, oh yes, Yunso.
So in a lot of the examples you wrote now, the number of vertices in the Coxeter graph is the same as dimension?
Yes.
Is that like the axes somehow?
Is it what?
Like is it related to like the number of axes and like how you rotate across them?
Yeah, so it will be the case that, well, okay, I guess maybe with this exception, but yeah, oftentimes the dimension will be, I think actually maybe that's true in all of these cases except for this one. And it does have to do with the fact that like the simple reflections are in some sense reflections that are like, symmetries of this regular polytope, and these reflections, if you consider like the normal vectors of these reflections, they will form a basis for the space that you're living in.
Colin, I think it's true for that one as well.
Oh wait, what?
It's true for the first one as well, because that's type AD, right? Not AD.
Oh!
Yeah.
Yes, it is still true here, and I was confused because, yes, Mitchell makes a good point. I should be calling this AD. Okay, so maybe I'll just mention that the subscripts here are indicating the number of simple reflections. And there's this weird fact that like AD is the same thing as the symmetric group SD plus 1, which is a little bit confusing, and it confused me just now. But of course, the reason that this is SD plus 1 is that you think of it as the symmetric group acting on D plus 1 objects, so that's where the subscript comes here. But in sort of Coxeter theoretic notation, the subscript would be D, which is keeping track of the number of simple reflections. Okay, thank you, Mitchell. Yeah, okay, so it is actually true in all of these cases. Okay. So I guess I was just mentioning that you can think of Coxeter groups as reflection groups, so maybe let me write that down. So Coxeter groups can be seen as reflection groups. And what I mean by a reflection group is you have some vector space, and you can define a reflection in some meaningful way. And then this is like some linear transformation on your vector space, and if you look at the group generated by these reflections, that's called a reflection group. So let me give an example of this. Actually, okay, I'm going to give an example of the affine symmetric group S3 tilde, and I'm going to draw it in a way that the reflections are actually affine transformations instead of linear transformations, but there's a way of going from affine transformations to linear transformations. But I think it's kind of nicer pictorially to think of it in terms of affine transformations. So let me show you what I mean. If you take S3 tilde, you can draw the infinite triangular grid. Okay, let's see how well I can do this. So imagine you have this infinite grid made out of little equilateral triangles. Okay, this is probably going to be bad, but we'll see.
Shouldn't we have a lot of practice?
What?
Shouldn't we have had a lot of practice
Yeah,
doing this?
yeah, I should have for sure had a lot of practice with this, but who knows? Maybe this will be. It's like not bad, I think.
No, yeah, it's really good.
Okay, cool. Yeah, I have had a lot of practice with this. Okay, so imagine this goes on, infinitely. You have this infinite triangular grid, and you can think of it as being made out of these lines, which are not exactly lines in the way that I've drawn it, but they should be. And for each one of these lines, you can consider the reflection through that line. You can say, okay, there's some kind of transformation that says, here's my line, and I'm just going to reflect space through that line. And you can look at all of the transformations that you can get by composing these reflections. In other words, look at the group of transformations generated by the reflections through these lines that I've drawn. And that ends up being isomorphic to S3 tilde. And actually, one way you can kind of realize it as being S3 tilde is if you choose one specific little triangle here. Let's see if I have colored chalk. Yes. So if I fix a little triangle here, then I can consider the three lines that touch that triangle. So there's like, maybe I'll do this one, and this one. And so those three lines give us three reflections, and those will be the three simple reflections that I wrote down whenever I did the affine symmetric group. So I could call this S0, and I could call this S1, and call this S2, And you can check that they will satisfy these relations from the affine symmetric group. And then actually you can realize any one of these reflections as a composition of some of these reflections that I or these three reflections that I wrote down. Okay? So this is kind of a hint of the geometric way of thinking about Coxeter groups. In fact, for any Coxeter group, there is some way of realizing it as a group of reflections in some sense. It's not always going to be like this. Sometimes it'll be like in a hyperbolic space, and then things can be kind of weird. Sometimes it'll be Euclidean space. Sometimes it's helpful to think of it as being like in spherical geometry. But in some sense, you'll always get a group generated by reflections for some appropriate notion of a reflection. Okay? Any questions up to here? Okay, let's see where we are. Okay, so maybe I can erase. I used to try to give lectures where I wouldn't erase anything and then like at the end everything would be written out. But I think that's a little difficult if I have to write large for the recording and also the class is 75 minutes. So I will erase. Okay. So one thing I mentioned last time is that if you have a Coxeter group such that the Coxeter graph is disconnected, then it will break up as a direct product. And so it's useful to consider just Coxeter groups where the Coxeter graph is connected. So we'll say W is irreducible if its Coxeter graph is connected. And in some sense, whenever you have some kind of a problem related to Coxeter groups, it's usually sufficient to just consider the irreducible Coxeter groups, because you can say, well, if I can understand this problem for irreducible ones, then by just doing direct products, I can understand it for general Coxeter groups. So many times you'll say, you'll see me say like, okay, let W be a finite irreducible Coxeter group, or an irreducible Coxeter group, or something like that, just assuming this. And let me give, so let me just say, so it is not a direct product of smaller Coxeter groups. And one more piece of notation, the rank of the Coxeter system WS, or sometimes I might just say the rank of W, although it really is depending on this S, is just the number of simple reflections. Okay, let me state the classification of finite irreducible Coxeter groups. I'm not going to, yes, Yuta.
Can an irreducible Coxeter group be a direct product of other groups?
Of other groups?
Yeah.
Oh, like not necessarily, well, maybe. But I actually don't know the answer to this off the top of my head.
Okay.
I should. And actually, when I was writing this, I was like, I hope someone doesn't ask me this question because I don't know how to answer it. But then you did. Okay, maybe, okay, I'll look that up. Okay, good question though. So, all right, let's talk about finite Coxeter groups. Right, so I mentioned here that like there are infinite Coxeter groups. You know, there's the affine symmetric group, but of course there are the finite ones like the symmetric group, the dihedral group. Like all of these that I listed here, these are finite Coxeter groups. So you might want to know like what are all of the finite Coxeter groups, and we have a list of them. And oh shoot, Dn is on this list. I'm going to make Dn a mystery because it's on the P set. I mean, okay, whatever. It's in the book anyway, so whatever. That question's going to be easy. So I'll just say it. Okay. This is the classification of finite, irreducible Coxeter groups. And this is due to Coxeter from, I think, 1935. And I'll just mention in this list that I'm going to write, the subscript will be the rank. So over there I had, you know, some notation, and every time the subscript was going to be the rank of the Coxeter group. So yeah, let me list this and then I'll make some comments about it. First of all, there's AN. So there are n nodes in this path graph, and all of the edges are labeled by 3, so I don't draw the labels. But this is also just the same as the symmetric group Sn plus 1. So there's often confusion, as you saw earlier, between like the fact that the subscripts are not the same, but this is just sort of an artifact of the fact that, like in this case, we're permuting n plus 1 things, so it makes sense for the subscript to be n plus 1. But if you're looking at the rank of the Coxeter group, it's n. Okay, then we have the hyperoctahedral groups that I mentioned before. There should be a 4 here. Okay, so in the P set, I ask you to draw the Coxeter graph of Dn. Here it is. It's basically like a path graph with a fork at the end. So actually, these are the 3 infinite families. Oh, sorry, there's another one, which is the dihedral groups. These are the 3 infinite families of finite Coxeter groups that aren't like super easy to deal with in most problems. Usually, I kind of ignore the dihedral groups because for most problems dealing with Coxeter groups, the dihedral groups are very easy to handle. And then, you know, usually it's interesting to think about A and B and Dn. And then there's some exceptional types. So there's E6, which looks like this. And then there's E7, which looks like this. And then there's E8, which looks similar. Then there's F4. Then there's, oh, I guess I put G2, yeah. G2, am I going too low?
You can maybe write one more.
Okay, there are 4 more. So we're gonna do this. G2, which is also known as I2 of 6. I'll explain why I'm doing this in a second. Then there's H3 that I mentioned over there. This is the symmetry group of the dodecahedron and also the icosahedron. And there should be a 5 here. And then there's H4. And then I2 of M, which is the dihedral group of order 2M. And you might wonder why I listed, oh, actually, it would have been yeah, let me do what Catherine suggested and write this down here. This is G2. I2 of 6. Okay. So you'll see that I put, I2 of 6 here, but it's also in this list. And the reason that I sort of separated these is that I mentioned last class that there are these semi-simple Lie algebras, which, we're not going to talk about Lie theory here, but it's good to be aware that there are these semi-simple Lie algebras, and each one has an associated Weil group, which is some special group associated to it. And it turns out that the Weil group is actually a Coxeter group, and these are the Weil groups of semi-simple Lie algebras. And then, so it's nice to have these over here, but then these are like exceptions that do not arise as Weil groups, except that like I2 of 6 is, and I guess also I2 of 2 and 3 and 4, but like I2 of 5 and I2 of 7 and I2 of 8 are not. Yes?
This is a naive question, but what happened to the letter C? Is it like?
Oh, this is a good question. Yes, what happened to the letter C? Sorry, can you remind me of your name?
Jack.
Jack, yes, okay. It's gonna take me a while to learn this, but okay, Jack. Right, what happened to C? The point is that when you have these semi-simple Lie algebras, there's a way of associating a collection of vectors to it called a root system. And if you look at the reflections through the hyperplanes orthogonal to the roots in this root system, you get this Weil group, which is this Coxeter group that I've written down. And so in the classification of these root systems, there is a Cn, and the root system for Cn looks very much like the root system for Bn. The only difference is the lengths of these vectors, which are called the roots. But when you look at the group is basically given by reflecting through the hyperplane orthogonal to a root. And when you're looking at the hyperplane orthogonal to a root, you don't care how long that root is. So in other words, the lengths of the vectors become irrelevant. And what ends up happening is that you have these two different root systems, Bn and Cn, but their Weil groups are the same. And so when you're just listing the actual groups, you don't need to list both of them. But yeah, that's a great question. Okay. So maybe one other thing I'll mention about this is that there are a lot of times in when people are studying Coxeter groups where they'll say, here's some problem that we want to prove some result about all finite irreducible Coxeter groups. And you say, okay, here's one way we could try to prove whatever this thing is about all finite irreducible Coxeter groups. We can check it for AN by thinking about this in terms of permutations, like very concretely and doing combinatorics with permutations. And then we can go to Bn, which we have some kind of combinatorial description for in terms of signed permutations. There's a similar way of thinking about Dn in terms of signed permutations with an extra restriction. And then you say, okay, we've checked it for An, we've checked it for Bn, we've checked it for Dn using combinatorics. Usually the dihedral groups are easy to take care of just kind of trivially. And then you say, we'll run a computer to check it for E6, E7, E8, F4, H3, and H4. And this works. This is a way of proving whatever this thing is, but oftentimes people will think this is kind of an unsatisfying way to prove it because you're very much relying on this classification, and you'd like to have some kind of an explanation of like, why is this actually true for all Coxeter groups rather than just checking case by case that it happens to work. So oftentimes you'll hear people talk about a type uniform proof of some result, and that's sort of saying that we have a proof that just uses Coxeter theoretic arguments and doesn't involve like checking case by case through the classification. And so I like type uniform arguments, but sometimes you have to just, you know, do it case by case because there's no better way. Or you can't think of a better way, I guess. Okay. Okay, so now let me, how much time do I have? 15 minutes? Yeah. Let's talk about reduced words. Okay, so reduced words are fun. I think last time I mentioned something like this formula for the number of reduced words for the decreasing permutation in Sn, which is this really beautiful formula due to Stanley. So there's a lot of interesting combinatorics coming from reduced words, and we're going to start talking about them. Okay. So, as before, WS is going to be a Coxeter system. So, just because S is a generating set for W, this just means that every element of W can be written as a product of simple generators. So every element of W can be written, or let me say, every element W in W can be written as a product of simple generators. And usually you want to write it as a product using the smallest possible number of simple generators, right? So I had this example last time where Ilaria gave me some permutation and I wrote down some reduced word and I said, well, I could just tack on like an extra S3 times S3 at the end, but you might think, well, why would you do that? It's like not really the simplest way of writing your permutation. So really we want to focus on the ways you can express W as a product of simple generators using the fewest number. And this is called a reduced word. So a reduced word which also has other names. Sometimes this is called a reduced decomposition. Sometimes it's also called a reduced expression. For W is basically it's a word over the alphabet S. So by this I just mean it's some formal product of these simple reflections, such that if you look at the element of the group actually represented by that product, it is this W. So that represents W and uses the minimum possible number of simple generators. So the number of these simple generators is called the length of W. So this minimum number is the length of W, and I'll denote it by L of W. So maybe one remark, oftentimes when people talk about permutations, like permutations in the symmetric group Sn, they'll say that n is the length of the permutation because it's like a permutation with n numbers in it. But I'm not going to do that because I don't want to confuse with this notion of length. So oftentimes if I'm thinking about a permutation in S5, I'll call it a permutation of size 5 instead of length 5 because the length is going to mean this. Okay? So let me state a lemma. So now I guess we're actually starting to like prove things. Use a lemma. So if you take any element W in W and any simple reflection S, you can look at the length of S times W. And this will be the length of W plus or minus 1. So in other words, when you multiply some element by a simple reflection, the length will either go up by 1 or go down by 1. And here's the proof. So you can check that the map sending W to its length, or sorry, to -1 to the power of its length is a homomorphism from the group W to the two-element group -1, 1, which I'm thinking is the two-element group Z mod 2Z or Z2. So then, this means that the length of, or maybe I should write it this way, -1 to the length of SW is, well, I could write this as -1 to the length of S times -1 to the length of W. But then, well, what is the length of S? S is just a simple reflection, so the minimum number of simple reflections needed to write S is just 1. You just write S. So this is 1. So this is the same as -1 to the length of W plus 1. And so this is saying that the length of SW has the same parity as the length of W plus 1. Okay, so length of SW is congruent mod 2 to the length of W plus 1. But notice that, okay, the length of SW is obviously less than or equal to the length of W plus 1. Because, well, by definition, this is the minimum number of simple reflections that I need to write SW, and the length of W is the minimum number of simple reflections that I need to write W. So if I write W as a product of simple reflections using this minimum number, and then I just add S on to the left of it, that gives me a way of writing SW as a product of simple reflections. So of course, the number of simple reflections I need here is at most 1 more than the number that I need for W. But then also, by a similar argument, you could say also, the length of W is the same as the length of S times W, because S times S is just the identity. And then if I just apply this argument with W replaced by SW, this is at most the length of SW plus 1. And so that means that the length of SW is greater than or equal to the length of W minus 1. So we've shown that the length of SW is between the length of W minus 1 and the length of W plus 1, and it has the same parity as length of W plus 1, so it has to be one of these two. Okay? Okay. Let me, I guess in the last 5 minutes, go through what this looks like in S3. So here's example in S3. Let me write a table. So we have element and reduced words. Yes.
Sorry, can you go over the proof of homomorphism?
Can I do what?
The proof of homomorphism.
Of the fact that it's a homomorphism?
Yeah.
Right, why is this a homomorphism? Yeah, maybe we can do that. Okay, so I'll postpone this. I could say this is an exercise. We'll see how this goes. Length of W, let's say VW. No, I want to say -1. Yeah, -1 to the length of VW should be, well, okay, length of VW is the minimum number of simple transpositions that I need to write VW. All I need to check is that this has the same parity as the minimum number of simple reflections for V plus the minimum number for W. Now, maybe this is non-trivial. Hold on. Okay, this is either easy or I just skipped it because I didn't want to go through it. And if it's the latter, then this is an exercise. Oh. Wait, what is the okay. Yeah. Okay. So this is written down in the book, but I'm not going to go through it. Okay. Is that sufficient? Okay, it's in the book. Yeah. So okay, let me go back and do S3. So we have element, reduced word, and length. Okay, so well, there's the identity element. It has sort of the empty reduced word, which, I mean, well, okay, maybe I'll write it as just like empty. And so the length is 0. And then, or maybe I should write this as 1, 2, 3 if I'm thinking of it in one-line notation. Then there's 1, 3, 2, which I could write as S2. And so its length is 1. And there's also 2, 1, 3, which I could write as S1, so its length is 1. And then I can do 3, 1, 2. So 3, 1, 2 you can get from 1, 3, 2, which is S2, and you multiply it on the right by S1, which has the effect of swapping the numbers in positions 1 and 2, so I get 3, 1, 2. So this has length 2. And there's 2, 3, 1, which is S1, S2. This has length 2. And then finally, I guess the interesting case is when you look at the decreasing permutation 3, 2, 1, I could write this as S1, S2, S1, but remember we have this braid relation that says this is also the same as S2, S1, S2, and these are the two different reduced words for this element, and so this has length 3. Okay? So we understand reduced words in S3, and then we can try to understand them more generally for other Coxeter groups. Okay, so I think that's all for today.